Okay, good morning. Now, yesterday we have seen encoder, that is linear encoder, to measure linear displacement of machine tools. We have also seen one video in which rotary encoders also they have discussed. Therefore, today we'll see this rotary encoder. See that this is the many light sources, or this light source is there. This disk is there. We are going to, I will play that video also. This disk is there which is having some slots on that disk. This is circular disk. It is mounted on the shaft. This is the hole for the shaft. Now when this light from light source light is emitted, therefore it passes through these slots, and these are the light detectors. It will detect light, and then signal is processed, and you are getting the correct angular position of the shaft in terms of degree. Therefore, this is nothing but rotary encoder. In that again, two types are there. Incremental rotary encoder. It is similar to the linear incremental encoder with the difference that the gratings are now on a circular disk. See that these are the gratings. Whatever lines you are observing, these are the grating. Now these gratings are on the circular disk. The common value of the width of transparent spaces is 20 microns. Therefore, whatever the size of these slots are there or gratings are there, its size is 20 microns, and space between the two gratings is also 20 microns. There are two sets of grating lines on two different circles which detect direction of rotation, and one can also enhance the accuracy of the sensor. Therefore, two sets are there. If you will observe carefully, these lines are not, these gratings are not continuous. Some break is there. Therefore, these two discs are there. On the two discs, gratings are there. There is another circle which contains only one grating mark. It is used for measurement of full circles. Next is absolute rotary encoder. See that this is absolute rotary type. Similar to the absolute linear encoder, the circular disc is divided into a number of circular strips, and each strip has definite arc segments. See that these are the, this circle or disc is there. It is divided into number of circles and again in number of arc segments. This sensor directly gives the digital output, that is absolute value. The encoder is directly mounted on the motor shaft or with some gearing to enhance the accuracy of measurement. To avoid noise in this encoder, a gray scale is sometimes used. A gray code, unlike binary codes, allows only one of the binary bits in a code sequence to change between radial lines. It prevents confusing changes in the binary output of the absolute encoder when the encoder oscillates between points. Therefore, we'll see the videos now.
Absolute encoders are used in many applications that require speed, position, angular displacement, and directional feedback. An encoder is a device that converts linear. Absolute encoders are used in many applications that require speed, position, angular displacement, and directional feedback. An encoder is a device that converts linear or rotary movement into digital or pulse signals. The most common type of feedback device is the absolute optical encoder.
Recording in progress.
An absolute encoder consists of four major components: a rotating encoder disc, a light source such as an LED, a detector as the light sensor, and a signal conditioner that converts the signals into square waveforms. The encoder disc consists of small, opaque, and transparent tracks mounted on a rotating shaft. Tracks are arranged concentrically around the center of the shaft. Photodetectors assigned to each track designate the resolution of the encoder. The higher the number of concentric tracks, the higher the accuracy. A light source located on the opposite side of the photocells passes light through a capture plate. As the encoder disc rotates, light is either transmitted or blocked according to the pattern. The received light provides a 4-bit word that indicates position of the actuator or device the encoder is mounted to. The most common types of numerical encoders are decimal, binary, and gray code. In a 4-bit encoder, there are 16 unique combinations for numeric code every 22.5 degrees. Gray code is designed where only one bit changes at a time, contrary to a binary system where one or more numbers change in the word. By changing more than one number of the word at a time in the binary system, the possibility of positioning errors is greater, leaving gray code the preference in precision applications. For robot applications, absolute encoders are commonly used for precise positioning operations. The actuator in this example demonstrates the function of the absolute encoder in operation. As the actuator moves to push the carton, the encoder provides feedback that it has reached the user-defined position. The actuator then moves back to the home position, verified by the encoder, and completing the cycle. Using feedback devices, control systems.
Okay, this is one video. Now we'll see another video.
Hey there. With 28% growth in demand and 2.7 million new jobs, data science is today a top focus for businesses across industries anywhere in the world. What if you had all that you needed for this opportunity? The PG Bootcamp in Data Science partnered with Purdue University.
Previously, we discussed what an encoder is and how it can be implemented in your application. In this video, we are going to discuss the various types of encoders and which encoder may be used for which function.
Please listen the video.
Before we get started on today's video, if you love our videos, be sure to click the like button below. Then make sure to click subscribe and the little bell to receive notifications of new RealParse videos. This way, you never miss another one. There are many types of encoders, but they basically fall into two main sensing techniques, those being linear and rotary. Within those categories, there are differing encoder measurement types, such as absolute and incremental. There are also various electromechanical technologies, such as magnetic, optical, inductive, capacitive, and laser, to name a few. There is a plethora of information regarding encoders, and it may seem hard to wrap your head around it. Descriptions like rotary or linear, optical and magnetic, absolute and incremental. We touch on a few basics to help you understand what's what and why. Let's first break these categories down a little and explain a couple of the many configurations. First, the linear encoder uses a transducer to measure the distance between 2 points. These encoders can use a rod or a cable that is run between the encoder transducer and the object that will be measured for movement. As the object moves, the transducer's data collected from the rod or cable creates an output signal that is linear to the object's movement. As the distance is measured, the linear encoder uses this information to determine the position of the object. An example of where a linear encoder may be used is for a CNC milling machine, where precise movement measurements are required for accuracy in manufacturing. Linear encoders can be absolute or incremental measurements. We will touch on absolute and incremental measurements a little later. A rotary encoder collects data and provides feedback based on the rotation of an object, or in other words, a rotating device. Rotary encoders are sometimes called shaft encoders. This encoder type can convert an object's angular position or motion based on the rotation of the shaft, depending on the measurement type used. Absolute rotary encoders can measure angular positions, while incremental can measure things such as distance, speed, and position. Rotary encoders are employed in a wide variety of application areas, such as computer input devices like mice and trackballs, as well as robotics. Rotary or shaft encoders, as previously stated, may be absolute or incremental. The next encoder, which is a position encoder, is used to determine the mechanical position of an object. This mechanical position is an absolute position. They may also be used to determine a change in position between the encoder and object as well. The change in position in relation to the object and encoder would be an incremental change. Position encoders are widely used in the industrial arena for sensing the position of tooling and multi-axis positioning. The position encoder can also be absolute or incremental. Optical encoders interpret data in pulses of light, be used to determine such things as position, direction, and velocity. Shaft rotates a disc with opaque segments that represent a particular pattern. These encoders can determine movement of an object for rotary or shaft applications, while determining exact position in linear functions. Optical encoders are used in various applications, such as printers, CNC milling machines, and robotics. Again, these encoders may be absolute or incremental. After explaining the main groups, you may be seeing a pattern. All the encoders basically do the same thing, produce an electrical signal which can then be translated to position, speed, angle, etc. Now that we have broken down the main groups, let's discuss the difference between absolute and incremental measurements. To discuss the difference between absolute and incremental measurements, we will use the rotary encoder type as an example. In a rotary absolute measurement type encoder, a slotted disc on a shaft is used in conjunction with a stationary pickup device. When the shaft rotates, a unique code pattern is produced. This means that each position of the shaft has a pattern, and this pattern is used to determine the exact position. If the power to the encoder was lost and the shaft was rotated, when power is resumed, the encoder will record the absolute position as demonstrated by the unique pattern transmitted by the disc and received by the pickup. This type of measurement is preferred in applications requiring a great degree of certainty, such as when safety is a primary concern, because the encoder knows at all times its definitive position based on the unique pattern produced. Absolute measurement encoders can be single-turn or multi-turn. Single-turn encoders are used for measurements of short distance, while multi-turn would be more suitable for longer distances and more complex positioning requirements. For incremental measure encoders, The output signal is created each time that the shaft rotates a measured amount. That output signal is then interpreted based on the number of signals per revolution. The incremental encoder begins its count at 0 when powered on. Unlike the absolute encoder, there are no safeguards regarding the position. Because the incremental encoder begins its count at 0 in startup or power disruption, it is necessary to determine a reference point for all tasks requiring positioning. In the previous video, when describing the use of an encoder for the purpose of counts, that example is a good example of an incremental encoder. Assume that the power has not been disrupted and you have turned on the conveyor and placed the machine. As the encoder is turning, the controller is receiving counts. Let's say the count range is 0 to 10,000. This is an incremental encoder, so the absolute position is not known. We just know that a full revolution of the shaft registers a count of 10,000. We'll place the object on the conveyor, and as soon as the entrance photo eye sensor detects the object, the current encoder count is captured. Let's say that number is 5,232. We will then capture the count with the object exiting and being detected by the exit photo eye. We'll say that the number is 6,311. So to determine the count of the full travel, we will subtract 5,232 from 6,311 and determine that the object travel is 1,079 counts. By this example, it is obvious that we do not know the absolute location of the object. We just know that the travel count from the entrance to exit is 1,079. That doesn't tell us that the object is 3 inches from the exit, just entering, etc. We just know that the object will enter, a count will be captured, and the object will exit, and again, the count captured. In the event that we did not see the object exiting within the allowable travel count, plus or minus a deadband, the machine will fault and the process will stop. There are many encoder variations out there, and we could go on for hours about the varying types. Hopefully, we have given you a basic understanding of what's out there, and when you may want to choose one particular type over the other. Want to learn PLC programming in an easy to understand format and take your career to the next level? Head on over to realpars.com.
Okay, now this is nothing but rotary encoder, incremental type and absolute type. You have seen difference also. In case of absolute encoder, slots are there on the disk, and in case of incremental encoder, there are different gratings or various slots placed readily on the disk. Incremental encoders are used to measure speed or velocity or distance. Therefore, this is nothing but rotary encoder. Now next is potentiometer. Potentiometer already from 12th standard or from 11th standard or maybe from 9th or 10th standard you are studying this potentiometer. A potentiometer, also referred as simply pot, is a variable resistance device that expresses linear or angular displacements in terms of voltage as shown in figures A and B. A indicates linear potentiometer, B indicates rotary potentiometer. It consists of a wiper that makes contact with a resistive element. See that this is the wiper, this arrow is there. This is the wiper. It makes contact with this resistance. It makes contact with this resistance. And as this point of contact moves, the resistance between the wiper and end leads of the device changes in proportion to the displacement. X and Q for linear and angular potentiometers respectively. Therefore, what they said, when this wiper is going to move along this resistors, sorry, when this wiper is going to move along this resistance either vertically upward or downward or in rotational manner in case of rotary type. Therefore, at that time, the resistance changes. Therefore, when this resistance change, there will be different output voltage you will get here. This output voltage V naught depends upon the position of the wiper or this distance x or this angle theta in case of rotary potentiometer. Therefore, this output voltage changes depending upon the position of the wiper, and this output voltage is calibrated in terms of linear distance or in terms of angular distance, and you are getting the linear position or angular position. Therefore, we will see this video, then you will understand it better.
Ever wonder why so many people say they want to learn guitar, but very few actually learn to play? It's simple. Too many people try to learn music videos and
Hello everyone, welcome back to the channel. Take a look at the image here. You will recognize it as one of the dials behind your steering wheel. Well, this is the fuel gauge which changes position depending upon the fuel level in the tank. The fuel in the tank is measured via a simple sensor called the potentiometer sensor. In this video, we will learn about the potentiometer sensor in more detail. The potentiometer was discovered by J.C. Poggendorff in 1841. Potentiometer sensor, in very simple terms, converts mechanical displacement into a voltage difference. So how does this happen? Let's find out. The working of a potentiometer is similar to that of a rheostat. Potentiometer sensor works on the principle that as we vary the length of the wire over a fixed distance, the corresponding resistance changes, provided that the wire has a constant current flowing through it. This is why they are also termed as resistive elements. To understand this, let us have a look at this diagram. Here 2 points are fixed, A and B. A movable wiper is present at point A, which can move along the length of the potentiometer. Let us name this as C. According to the principle mentioned earlier, as the wiper moves, it changes the resistance. With a change in resistance, a potential difference is developed. The potential difference helps us in measuring displacement. If V is the total voltage and R is its total resistance, then V0 is the measured voltage over the resistance R0. Therefore, V0 by V equals R0 by R. Here we see that the track has a constant resistance per unit length. That is, it also has a constant resistance per unit angle. This means that an angular displacement can also be measured as the output is proportional through the angle by which the slider has rotated. Potentiometer sensors can be used to measure both linear and angular displacement as a result. Potentiometer sensors find their application in electric guitars too. The sensor here is wired as a volume control. By sending a part of the current to ground, it controls the amount of electric signal received by the amplifier. Potentiometer sensors were also used in TVs to adjust the brightness, contrast, and color response. It affected the synchronization between the received picture signal and the receiver's internal sweep circuit. Potentiometer sensors have the following advantages. They find the exact value of the potential difference between any two points, and they are easy to use. But they have a couple of disadvantages as well. They experience excessive wear due to moving parts, low repeatability, and limited frequency response. Well, that's all about potentiometer sensors. We'll see you again in the next video. Until then, bye.
Okay, this is nothing but potentiometer sensor, that is V naught divided by VR. V naught divided by VR is equal to R naught divided by this x length. Therefore, we are knowing any three values, and we'll get that output voltage V naught in case of linear potentiometer and rotary potentiometer. Therefore, next is now LVDT, linear variable differential transformer. Now, the linear variable differential transformer name itself indicates that it is used to measure linear displacement because the word linear is there. And variable differential transformer, variable, why it is known as variable? Because here in this LVDT, it consists of two windings, primary coils. See that, primary coil and secondary coil. Therefore, as this magnetic core, movable ferrous core, moves either towards left or either towards right, therefore voltages are induced in the primary coil and secondary coil, and there is difference between the two voltage. That is, value of the voltage induced in the primary coil does not equal to the value of the voltage induced in the secondary coil. Therefore, now we'll see this linear variable differential transformer. The linear variable differential transformer is one of the most used displacement transducers, particularly when high accuracy is needed. It generates an AC signal whose magnitude is related to the displacement of a moving core. See that, whatever I have told, when this core, iron core or ferrous core moves, therefore a signal is generated, and that signal is nothing but difference between the voltages of the, it is directly calibrated in terms of the difference between the voltages of the primary coil and secondary coil. The basic concept is that of a ferrous core moving in a magnetic field, the field being produced in a manner similar to that of a standard transformer. There is a central core surrounded by two identical secondary coils and a primary coil as shown in figure. Therefore, this is the central core is there. It is surrounded by primary coil and secondary coil. As the core changes position with respect to the coils, this is the core. This is magnetic core, ferrous magnetic core. It is surrounded by primary coil and secondary coil. As the core changes position with respect to the coils, it changes the magnetic field, and hence the voltage amplitude in the secondary coil changes as a linear function of the core displacement over a considerable segment. Therefore, when this core moves, because of this magnetic field, voltages induced in the primary coils and secondary coils is different. Now I will tell why it is different. It depends upon the portion of the core in front of that coil. If maximum portion of this core is in front of secondary coil, therefore maximum voltage is induced in secondary coil, minimum voltage is induced in the primary coil. That is, if this core is towards rightmost position or to the leftmost position, and when this core is exactly at the center in front of primary coil, therefore voltage induced in the primary coil is more than that of the secondary coil. Therefore, it depends upon the portion of the core in front of the coil. Therefore, as the core changes position with respect to the coils, it changes the magnetic field, and hence the voltage amplitude in the secondary coil changes as a linear function of the core displacement over a considerable segment. Therefore, this is nothing but linear variable differential transformer, and that voltage difference between primary coil and secondary coil is directly calibrated in terms of the displacement. Therefore, Next is also a rotary variable differential transformer or RVDT operates under the same principle as the LVDT, is also available with range of approximately plus or minus 40 degree. Therefore, this is nothing but linear variable differential transformer. See that this is the iron core, movable ferrous. Ferrous means iron. It is connected to the object whose displacement we have to measure. These are the primary coils, two primary coils. These are the secondary coils. Now we'll see the videos.
Hey guys, welcome back to the channel. As we know, a pilot gives several commands to the aircraft during a flight. These commands are recognized by the computer and then the designated actions are taken. These commands are in terms of the movement of the flight. For example, a command like yawing will result in a side-to-side movement of the aircraft. Similarly, pitch changes the vertical direction of the aircraft. Now, these actions have to be continuously tracked so that the movement of the aircraft is balanced. This is where the role of an LVDT comes in. LVDT, or Linear Variable Differential Transformer, is an electrical device that measures displacement. The LVDT here tracks the length by which these movements take place. It then reports it back to the computer by its feedback mechanism. This changing movement is then viewed by the flight operator. So how does this mechanism work? Let's find out. The primary principle behind an LVDT is mutual inductance. Mutual inductance was discovered by Michael Faraday in 1831. He discovered that a current carrying coil having a magnetic field around it develops an induced EMF in a coil adjacent to it. He termed this phenomena as mutual inductance. Before jumping into the working of LVDT, let us understand its construction. An LVDT consists of a hollow cylinder. On this hollow cylinder, a primary coil is wound at the center. Two secondary coils having an equal number of turns are wound at equal distance from the primary coil on the cylinder. Through the center of the cylinder, a magnet is held with the help of a long non-ferromagnetic shaft or push rod, which is allowed to move freely inside the cylinder. The primary coil is connected to an AC source. The current is passed over the primary coil, and due to mutual inductance, an induced EMF is developed on the secondary coils. The induced EMF in secondary coils S1 and S2 are taken to be E1 and E2 respectively. As you can see in the animation, when the magnet is placed at the center of the cylinder, an equal amount of EMF is developed on either side of the secondary coil. Since there is no movement of the coil here, the net EMF is zero. This is called the null phase and is given by E out equals E1 minus E2 equals 0 volts. Now, when the coil is moved towards one side, for example S1, the secondary coil becomes more strongly coupled than S2. This means that there is a larger EMF developed in S1 than in S2. The output of this is given by E out equals E1 minus E2. Conversely, when the core moves towards the secondary coil S2, the output is given by E out equals E2 minus E1. Thus, by measuring the change in EMF, we can calculate the distance by which the core is moved. There are some qualities of LVDT that make them very efficient in the industries. Apart from being extremely reliable, the repeatability of LVDT is extremely high. Since the core is not fixed to any part, there is no friction. The setup is placed in a closed configuration, allowing no contamination or moisture to enter. Hence, these devices can be used for a very long period of time. LVDT, apart from aircraft, find their usage in measuring fuel levels and nuclear reactors. They are also used for weight-sensitive applications. Well, that's all on LVDT. Stay tuned for more videos. Until the next one, bye.
Now next video.
My job is to make college easier because students have a lot. Please.
Today's session, we are going to learn about linear variable differential transducer, that is LVDT. It is used for measurement of displacement. It consists of insulating hollow cylinder made up of bakelite. On insulating cylinder, two windings are wound called as primary and secondary windings. The primary windings is wound at center of insulating cylinder, and on either side of primary winding, two secondary windings S1 and S2 having equal number of turns are wound. Here the direction of secondary windings S1 and S2 are exactly opposite to each other. Inside the insulating cylinder, magnetic core is placed, which is free to move in either of direction. When AC supply is given to primary winding of Lvdt, it produces magnetic flux which completely sparks to secondary windings S1. While completing the path, flux produced by primary windings of Lvdt linked to number of conductors of secondary windings. Therefore, according to Faraday's law of electromagnetic induction, EMF is induced in secondary windings. When core is at center position of insulating cylinder, magnetic flux linking to coil S1 and S2 has same value. Therefore, EMF induced in coil S1 and S2 are also equal, so that the differential output measured between two secondary terminals is zero. Here, when core is moved towards left side, then flux linking to coil S1 will increase. At same time, flux linking to coil S2 decreases. Hence, EMF induced in coil S1 is greater than that of S2. As a result of which, output measured between secondary terminals is in phase with primary voltage. When core is moved towards the right side, then flux linking to coil S2 is more as compared to coil S1. That is, EMF induced in S2 is greater than EMF in S1. Hence, differential output measured between secondary terminals is out of phase with primary voltage. Thus, differential output measured between two secondary terminals of Lvdt is directly proportional to displacement of magnetic core. In this way, we can measure displacement of iron core by linear variable differential transducer.
Now, next point, that is resolver. A resolver uses the same basic physical principles as an electrical transformer. Resolvers typically use copper windings in its stator and a machined metal rotor. The inductive coupling between the windings varies according to the angular position of the rotor. See that this is the rotor, it is the metal rotor, this is the primary winding, these two are the two secondary windings S1 and S2. Therefore, inductance means EMF, that EMF induced in the two secondary windings will depend upon the position of this metal rod or this rotor, metal rotor. The resolver is energized with an AC signal, means this through the primary windings. As we have seen in case of Lvdt, AC signal is provided and the resulting output from the transducer windings is measured to provide an electrical signal which is proportional to angle. Therefore, that resulting signal will be depends upon the voltages or that EMF induced in between the two windings, that is two secondary windings S1 and S2, depending upon the position of this metal rotor, because this metal rotor, it is the rotating part. The resolver is energized with an AC signal and the resulting output from the transformer windings is measured to provide an electrical signal which is proportional to angle. A typical resolver has three windings, a primary winding and two secondary windings. The windings are created using copper wire and are formed on the resolver's stationary element, that is the stator. The primary wire acts as the input for an AC drive signal and each of the secondary windings are used as pickup or receive windings. In the diagram above, the rotor is made from a material such as steel or iron and is arranged to relative to the windings and therefore will couple varying amounts of energy into the secondaries depending on its angle of rotation. Therefore, as we have seen in case of Lvdt, same case is here, that is when this metal rotor, when it will start rotating, therefore if maximum portion will be in front of S2 winding or secondary winding S2, therefore maximum EMF will be induced in the S2, minimum will be induced in the E1. that is S1. Therefore, that output EMF is equal to E naught is equal to ES2 minus ES1. If that maximum portion of this metal rod is in front of S1, then output voltage E naught is equal to ES1 minus ES2. Sorry, output EMF is equal to E naught is equal to ES1. That is whole EMF induced in the secondary winding 1 minus EMF induced in the secondary winding 2. Therefore, depending upon this output EMF, that output EMF is directly calibrated in terms of angle of rotation, and directly we are getting the angle of this metal rotor. Now we will see these two videos so that you will understand it clearly. Please see it.
This milling machine has several axes driven by a servo motion system. Actually, as a feedback sensor, there is a resolver installed. But how is this resolver working? After this video, you will have a better idea. The resolver consists of a stationary part called stator and a revolving part called rotor, which is attached to the motor shaft. The primary winding of the stator is connected to a high-frequency sine signal. This sine signal is transmitted to the rotor winding because the stator's primary winding and the rotor winding act together like a transformer. Furthermore, we can name the rotor winding also as reference winding. The relative magnitudes of the sine and cosine voltage are measured to determine the angle of the rotor relative to the stator. To get an output signal, we have two secondary stator windings, a so-called sine and a cosine winding, which are displaced angularly to each other by 90 degrees. So let's mount this resolver to the motor shaft and apply a high-frequency sine signal to the stator primary winding. The pulsating alternating magnetic field of the rotor winding now induces an alternating voltage in the measuring windings sine and cosine. Their amplitudes, however, depend on the angular position of the rotor. If the rotor winding and the measuring winding are parallel to one another, the magnetic rotor field completely passes through the measuring coil. Therefore, the induced voltage is maximum. And at 0 degree shaft angle, the cosine wave also has its maximum. If the rotor winding and measuring winding are at a right angle to each other, no voltage is induced. Let's turn the motor shaft 90 degrees. We can prove all these statements. So, let's change the time base of our oscilloscope and watch the measuring signals. What you see now is that you get a modulated sine and a cosine measuring signal, which are also called envelope curve. It's now up to the resolver digital converter, RDC, to evaluate the current rotor position and the rotational speed from these signal curves. Well, unlike encoders, resolvers have no electronic components and therefore robust against soiling, vibrations, and work safely even within a wide temperature range. This makes them highly reliable and environmentally resistant. Watch also our next videos.
Please see this next video.
a lot of times I used to get very nervous speaking to overseas clients because I couldn't understand what they were saying. And
दोस्तों इस ट्यूटोरियल में हम समझेंगे रिजॉल्वर जो है वो कैसे काम करता है। तो जैसे कि हम एनिमेशन में देख सकते हैं जो हमारा स्पीकर है वो यहाँ पे है और इसकी जो 3 वाइंडिंग है जैसे कि एक्साइटेशन वाइंडिंग, साइन वाइंडिंग और कोसाइन वाइंडिंग जो है वो यहाँ पे है। रोटर जो है वो अटैच है शाफ्ट के साथ और इसकी जो वाइंडिंग है उसके जो 2 पार्ट्स हैं वो इसके दोनों साइड्स में हैं। जैसा कि हम देख सकते हैं रोटर वाइंडिंग का जो एक पार्ट है वो अलाइन है एक्साइटेशन वाइंडिंग के साथ और दूसरा जो पार्ट है रोटर वाइंडिंग का वो अलाइन है साइन वाइंडिंग के साथ। दोस्तों ऐसा कभी नहीं होगा कि एक ही टाइम पे जो रोटर की वाइंडिंग है वो पैरेलल में हो साइन वाइंडिंग के साथ या कोसाइन वाइंडिंग के साथ। एक टाइम पे या तो ये साइन वाइंडिंग के पैरेलल में होगी या फिर ये कोसाइन वाइंडिंग के पैरेलल में होगी। दोस्तों जब हम रेफरेंस सिग्नल जो है वो एक्साइटेशन वाइंडिंग को देते हैं DC 7 वोल्ट 10 किलोहर्ट्ज का, तो जो रोटर की वाइंडिंग है उसको इलेक्ट्रोमैग्नेटिक डायरेक्शन से, और जब हमारी रिजॉल्वर की शाफ्ट जो है वो रोटेट करती है और रोटर की वाइंडिंग और जो साइन वाइंडिंग है वो आपस में पैरेलल में हो जाती है और उस कंडीशन में जो मैक्सिमम वोल्टेज जो यूज होती है वो साइन वाइंडिंग में होती है और हमें आउटपुट साइन सिग्नल मिलता है। जब हमारा रोटर फर्दर रोटेट करता है और रोटर की वाइंडिंग आपस में पैरेलल में आ जाते हैं, जो मैक्सिमम वोल्टेज है वो इंड्यूस्ड होती है कोसाइन वाइंडिंग में और हमें आउटपुट कोसाइन सिग्नल मिलता है। जो आउटपुट सिग्नल मिलता है वो 3.5 वोल्ट 10 किलो हर्ट्ज में मिलता है साइन और कोसाइन सिग्नल में। दोस्तों जैसे कि हम यहाँ पे देख सकते हैं कि रोटर को हम किसी भी हार्ड वायर के साथ हम इसको सप्लाई नहीं दे रहे हैं। इसमें जो वोल्टेज इंड्यूस हो रही है वो हो रही है इलेक्ट्रोमैग्नेटिक इंडक्शन से। इससे हमें फ़ायदा ये होता है कि हमें कम्यूटेटर और स्लिप रिंग को यूज़ करने की ज़रूरत यहाँ पे नहीं होती। इससे इसकी जो लाइफ है रिजॉल्वर की वो इम्प्रूव होती है और इसमें लेस मेंटेनेंस की जरूरत पड़ती है। दोस्तों रिजॉल्वर की वर्किंग को समझने के लिए यहाँ पे हम कुछ एग्जांपल की हेल्प लेंगे। तो 90 डिग्री शाफ्ट एंगल के ऊपर जो रोटर की वाइंडिंग है वो पैरेलल होगी साइन वाइंडिंग के साथ। तो इस कंडीशन में जो हमें सिग्नल मिलेगा वो मैक्सिमम सिग्नल मिलेगा साइन सिग्नल, और इस कंडीशन में जो कोसाइन सिग्नल रहेगा वो ऑलमोस्ट 0 रहेगा। अगर हम बात करें 0 डिग्री शाफ्ट एंगल की, तो इस कंडीशन में जो रोटर की वाइंडिंग है वो पैरेलल में रहेगी कोसाइन वाइंडिंग के साथ। तो इस कंडीशन में जो मैक्सिमम वोल्टेज इंड्यूस होगी वो कोसाइन वाइंडिंग में होगी और जो मैक्सिमम हमें जो सिग्नल मिलेगा वो मिलेगा कोसाइन सिग्नल। अगर हम बात करें साइन सिग्नल की, तो ये ऑलमोस्ट 0 होगा 0 डिग्री शाफ्ट एंगल के ऊपर। अगर हम बात करें आउटपुट वेवफॉर्म की, तो दोस्तों वो कुछ इस तरीके की बनेगी। जैसा कि हम जानते ही हैं कि 0 डिग्री के ऊपर जो साइन होता है वो 0 होता है, तो यहाँ पे जो साइन सिग्नल है वो 0 रहेगा और 0 डिग्री के ऊपर जो साइन सिग्नल है वो मैक्सिमम रहेगा। 90 डिग्री के ऊपर जो साइन सिग्नल है वो मैक्सिमम रहेगा और 90 डिग्री के ऊपर जो साइन सिग्नल है वो 0 रहेगा। तो जो आउटपुट वेवफॉर्म है वो कुछ इस तरीके की बनेगी। दोस्तों अगर हम बात करें रिजॉल्वर के कनेक्शन की PLC के साथ, तो हम रिजॉल्वर को सीधा कनेक्ट PLC के साथ नहीं कर सकते। इसके लिए हमें एक डिवाइस की जरूरत पड़ती है जिसको हम कंट्रोलर कहते हैं। कंट्रोलर का बेसिकली काम होता है रिजॉल्वर को हाई फ्रिक्वेंसी इनपुट देना और इससे साइन और कोसाइन सिग्नल जो है वो लेना है, PLC को देना है। दोस्तों इस ट्यूटोरियल में बस इतना ही। इसके साथ हमारा जो रिजॉल्वर का टॉपिक है वो खत्म होता है। करता हूँ कि आपको इससे काफी अच्छी क्लैरिटी मिली है।
Okay, now we'll stop here. I have taken your attendance. Now in the next lecture, we'll see tachometer, Hall effect sensor, strain gauge based sensors, Wheatstone bridge, that I will cover. Okay, thank you very much. Thank you. I have taken your attendance. Please don't write in the chat box.